Paul and I are going to start out with an introduction to aquatic sciences KGML, and I'm going to let Paul take it away for the first two slides.
Great, thanks, Allison, and welcome everybody to the aquatic sciences session. And as Allison said, she and I are going to tag team and hand off this introductory talk between each other. We have a few goals for the introduction. One is to define KGML within the context of aquatic sciences and identify some of the functions KGML can perform in our field and relate that functionality to the scientific process. We'll preview how current work exemplifies the different applications and approaches to KGML. And to get you thinking about some of the science addressed in the presentations, we'll point to frontiers in the applications of KGML and aquatic sciences. By the end of the session, we also hope that you're inspired to think about ways in which machine learning may be combined with your expertise to advance aquatic sciences. Next slide, please. So the text graphic that you see on the first slide in the upper left of this slide as well is meant to symbolize the inseparability of knowledge guidance and machine learning. There's a perception that machine learning, when it's used alone, can be an unguided black box used for expediency just to get better predictions. However, all aquatic science machine learning applications have at least some knowledge guidance, as illustrated here by the fact that even the stick figure in the cartoon, the stick figure's attempt to do fully data-driven modeling still requires that they stir the pile and somehow recognize when it looks right, which cannot be done with knowledge of how it should look in the first place. So our goal with KGML is to be intentional about how traditions of our discipline can work together with machine learning techniques in lots of different ways, ranging from how ideas are conceived to how algorithms and workflows are built and how results are interpreted. Effective KGML is also built on a foundation of understanding among disciplines, and so there's an important interdisciplinary component that deserves attention too. Thus, for our purposes today, we define KGML as the purposeful integration of data science with aquatic sciences knowledge that takes many different forms that you've seen already in the workshop and that we'll survey in this talk. Next slide, please. These are just a few of the benefits and their importance to aquatic science, and this echoes some of what you've seen in Bipin Kumar's opening talk and previous talks too. Accurate and explainable predictions are important to our stakeholders, whether we're predicting floods or the probability of a harmful algal bloom or an anoxic fish kill event. Data availability can be a big problem in our field, especially for chemical and biological variables. Often we don't have the necessary data to fully use new deep learning techniques. In other words, our big data often are big in their diversity rather than in their volume. And KGML has been shown to help address this problem. And this capacity also translates into confidence in applying models trained on data-rich systems to data-poor systems. Updating our understanding of the way the world works is foundational to science. KGML provides opportunities to test our conceptual and quantitative models by providing a range of model insights, from parameterization to model structure to clues about what may be ecologically important, but maybe that we've forgotten to put in our models in the first place. Finally, at least for this list, KGML provides a means to avoid that rabbit hole of increased process model complicatedness. Models can take on a life of their own and become way over parameterized. It's true for both machine learning and for process-based models. And the architectures of KGML can be highly flexible, allowing us to use parsimonious models from aquatic sciences, along with machine learning algorithms to attain better performance that we get from either approach alone. Next slide, please. So we are desperate for advancements in our field. The challenges put forth by the National Academy in their 2018 report are just some of the many challenges that we're facing. The difficulty in understanding how to address these challenges becomes compounded as we move from the physical realm up through the chemical and biological realms, in part because the data become more sparse and the system characteristics become more complex. We'll see a number of examples, especially relevant to physical variables such as water temperature. We have fewer examples in chemistry and biology, but please do go back and have a look at the posters, which do have a couple of examples in water quality. Both our questions and our data are big. Sometimes our data volumes aren't big, but at least they're big in their heterogeneity. And we need these approaches such as KGML that enable us to harness these data to meet the very real needs. Alice.
So there are a number of ways that we can use modeling to address these big questions, these really real aquatic sciences needs. And here is a schematic of a couple of the major ways that we can use any kind of model. So we can go from observed data on the left, and we can use models to make inferences about the underlying processes and parameters of a model, usually by fitting or calibrating a model. And these inferences provide one form of understanding and answers. And then we can also use those fitted models to make predictions, which lead to a different form of understanding, which is grounded more in patterns and scenarios. For example, here are the trends in lake clarity over the last few decades, or if you add a riparian buffer near this stream, here are the changes you can expect in biodiversity. People who are new to machine learning sometimes make the oversimplification that it's all about predictions. But in fact, machine learning offers much more than that. It can expands the number of pathways that we can use to get from observations to understanding by quite a few. So on top of these pathways in gray, we can now also go straight from observations to predictions without defining specific parameters to calibrate. And we can extract inferences from predictive models using feature importance and explainable AI methods. There's also this entirely new step of distillation made possible by methods like clustering and autoencoders and other forms of dimension reduction, which take a complex data set and make sense out of it. So now we can remember better, we can discuss, we can develop hypotheses based on that more distilled information. And then all of these pathways, whether they're in gray here or blue, can be enhanced with knowledge-guided machine learning. KGML allows us to make more accurate predictions, lets us make richer inferences about the underlying processes, and allows us to distill information more meaningfully into information that we can digest. In the aquatic sciences, we're making use of all three of these pathways regularly to answer our science questions. And so here I've taken the collection of posters and talks from this session and some other aquatic sciences talks within the workshop and just clustered them into these three pathways. One thing that we can see here is that our strongest representation is in this prediction pathway. So yeah, prediction is important for machine learning, but almost 2/3 of today's presentations also use inference or distillation to get down to information. What this says to me, this diversity of KGML approaches, is that there's almost no question in the aquatic sciences that can't benefit from KGML. And that brings us back to this starting idea from the presentation, which is that it's one thing to just stir that pile, like to apply knowledge guidance without acknowledging what you're doing. But it's much more valuable to use knowledge guidance intentionally and to use more powerful tools than a canoe paddle. Given that there are so many pathways from observations to understanding, it's also no surprise that we see a diversity of approaches to knowledge guidance. And so in the next 6 slides, I'm going to walk through some of the recurring themes that we see in this session for how aquatic scientists are using knowledge guidance with intention to support their research. So knowledge guidance begins at the very start of the modeling process in the data preparation phase. Most of the presentations you'll see today will include some expert-based selections of the predictors that are going into the model. And some efforts are also using feature engineering to extract even more targeted information. For example, Kazito Masaba created these high-level descriptors of storm events rather than passing in the raw time series of precipitation to provide a more meaningful input variable. And Carlotta Valerio's poster showed engineering of the variables that the machine learning model was asked to predict, in those cases, metrics of species richness for native or alien species. Another approach to knowledge guidance addresses the guts of the machine learning model itself. So here researchers are designing the structure of their machine learning models to reflect the structure of the real world. Several of today's presentations describe uses of LSTMs or other time-aware models to predict or distill time series variables. Sam Oliver and Janet Barclay discussed the use of graph convolution to reflect spatial relationships among stream reaches. And then Shuki Lin shared this approach to chlorophyll prediction that involves some intermediate variables for nutrient concentrations. So those are predicted in this first machine learning step and then used as input into that second learning step that predicts chlorophyll A. Another way that we can do this is embed knowledge within the loss functions that we use to train our models. And this is an area where we've seen a lot of creativity in recent years and hope to see more in the future. Loss functions that encourage mass balance or energy balance have been used in several recent studies and have a lot of power. And then Janet Barclay today is going to share a couple of new metrics that are enforcing this situation appropriate temporal signal, a seasonal pattern in the relationship between water temperature and air temperature that should vary with how much groundwater influence there is in a site. And so her loss function terms enforce that fairly complicated relationship. And then Robert Ladwig has proposed a loss function term that leverages the observed power spectrum of dissolved oxygen concentrations, similar to what Paul Hanson shared last year for phosphorus, but this time looking at dissolved oxygen and aiming to create a more realistically smooth time series of predictions. So going from this black line here without that loss function term to the purple line here once we've added in that effectively smoothing power spectrum loss term. We can also make use of process-based models as a source of knowledge guidance. And so these can be used to pre-train a machine learning model before fine-tuning that model on observations, as Sam Oliver and Janet Barclay are doing. And they can also be the focus of a study such as Moritz Fegel's, where he predicts residuals between observations and process-based predictions to understand where and why the process-based model does better or worse. Knowledge guidance comes into play around how our models are assessed as well. For example, Titan Alkan looked not just at the accuracy of his wave height predictions compared to observations, but also at whether those predictions were capturing realistic trends and extremes in wave heights. Sam Oliver assesses her water temperature forecasts based in part on their ability to predict exceedances of this ecologically meaningful temperature threshold for fish health. Model evaluation on its own doesn't constitute knowledge guided machine learning in the sense that it doesn't always get into the machine learning model, but it can informally. It does in the sense that as modelers are iteratively developing their models and learning from assessments like these, they can then adjust things like their model structures or inputs or loss functions to better capture these metrics that they do want to hit. And lastly, from me, today's presentation shows how we can use machine learning also to strengthen our conceptual models in the aquatic sciences. Several studies today use feature importance assessments or attribution to learn about the drivers of water quality and other ecosystem properties. Heather Wander's poster showed uses of autoencoders and clustering to identify common and meaningful patterns in lake areas over time. And Anush Karpatni will be presenting later on the use of explainable AI, looking to learn why their machine learning model sometimes disagrees with experts on which fish species is present in a photo, which has led to the discovery of new fish species traits. All of these techniques I've covered are about enhancing these model pathways, all of them, from observations through to understanding. In other words, they're using knowledge-guided machine learning to guide the creation of new knowledge. To me, this diversity of pathways and this diversity of approaches to KGML all means there are huge opportunities here, both to answer these pressing aquatic sciences research questions that we have, and also to continue discovering new ways, new methods to better answer those questions.
So Alison and I have put 3 resolutions on the table for this afternoon. First, let's push ourselves. Many important advances in aquatic sciences have come from borrowing ideas and methods from other disciplines and from collaborating at the seams between disciplines. And KGML is inherently interdisciplinary. Let's be creative in how we envision use of these techniques while always being mindful of the best we've learned from our discipline. And in the spirit of some of the caveats that, for example, Peter Dubin raised earlier about KGML, let's also keep a critical eye on the pros and the cons of the technique. And finally, the water's warm and welcoming. So please do wade in with us and join us. You may imagine there are some monsters lurking beneath the surface. And this is a photo of Pineview Reservoir in Utah. And it was falsely rumored that there were bull sharks that were introduced into the lake. But really, I think what's in there are these endemic piscivorous fish. They're all part of the ecosystem. They're meant to be there, and they're not so scary once you get to know them. So come on in. It's a safe space in which to play and to have fun. And the last slide. So these are the kinds of issues that are beginning to be addressed by the posters we've seen in the presentations that we're about to hear. These are familiar and difficult frontiers in aquatic sciences. They include interpreting and understanding machine learning output, improved predictions, and a deeper understanding of uncertainty and how that feeds back to, for example, model design, the collaborative process that's needed for effective interdisciplinary teams, and what we can do to foster those collaborations. These frontiers are consistent with the larger goals of science. I think we've seen these issues popping up all week long, and I suspect we'll see them come in other forms tomorrow as well. And KGML provides an exciting and a fun new context to make progress. So as Alison had said earlier, thank you so much to our poster presenters, and those posters are still up, and please go back and have a look at the posters if you haven't had a chance to do that. And thank you in advance to our presenters who will be showing their work here shortly. So that's it for the introductory talk. Alison, I'm not sure we have time for any questions, and we should probably get set up for our first talk.